So we skipped talking about intensity last lecture, but for sound waves, it's actually pretty interesting. We know that waves carry energy from one place to another, and the intensity of a wave is one way to quantify that energy. So if we consider the particle velocity, v, x, and t, that's given by the partial derivative of y as a function of x and t with respect to t, right? And so if we consider a sinusoidal sound wave, right, a cosine of kx minus omega t, then that's given by, this particle velocity is given by omega a sine kx minus omega t, right? Because the omega comes out, took a derivative with respect to t. So we know that power is the rate of work. We often talk about it Newton meters per second. It's the rate of work. Work is force through distance, and then per time is the rate. Or another way of saying that is this is force times velocity. So force times velocity, right? We have the particle velocity, but what's the force at play here? Well, recall that pressure is force per area. So we can use our pressure and velocity expression to get an expression for the power. So if we say the pressure is a function of x and t, that's force per area. And then we have our velocity as a function of x and t. Expanding this, we see bulk modulus K A sine kx minus omega t times our velocity, omega a sine kx minus omega t. Which gives bulk modulus K A squared omega sine squared kx minus omega t. I'll tell you now, intensity is defined as the time average value of the power. Time average value of the power here would be the average of what this function is. So sometimes it's so let's see. So it's sinusoidal. And about half the time it's in this region, and about the other half of the time it's in that region, right? And so intensity here would be 1/2 b k a squared omega, right? Or using omega is equal to vk, and v squared is equal to bulk, it's not beta, it's bulk modulus divided by the density, what we wrote up here, right? Then we can write this in a different way. We can write the intensity is equal to 1/2 square root of rho beta omega squared a squared. And this can also be expressed in terms of the pressure amplitude, what we defined earlier as P max, right? And so we can say I is equal to P max squared divided by 2 rho V, or equivalently P max squared divided by 2 square root of rho bulk modulus. So lots of these different expressions can be useful. I'll box this guy in because that always helps to indicate that something's important. But the other versions of the expression are also useful as well. So one last statement about intensity. The unit for sound intensity is the decibel, which is 1/10 of a bell after Alexander Graham Bell, who is the inventor of the telephone. Because the human ear is sensitive to such a wide range of frequencies, we use the logarithmic scale for sound intensity, which is given by this beta, which is not the Boltz's modulus now. So beta is given by 10 dB decibel. That's not the Boltz's modulus either. Is log I over I naught. And this table gives some example sounds with their corresponding decibel levels and intensity that I will copy on over to us here, and we can take a look at some examples. All right. So at the bottom of the table, 0 decibel is about as low as we can hear at 1,000 hertz. And the intensity is 10 to the negative 12th. A rustle of leaves, pretty quiet sound, or an average whisper, we're getting to 10 and 20 decibels. And you would think that a military jet aircraft 30 meters away, it's pretty close as far as that sound goes, would be, orders of magnitude higher, but because it's a logarithmic scale, you've only gotten up to 140 decibel. So I guess all that's to say that when you hear sound levels reported, you have to be careful because it's not a linear scale, it's a logarithmic scale. And so going up 5 decibels in sound can actually be pretty substantial. Yeah. So next, we are going to talk about beats, resonance, and interference.